Hi, welcome to the presentation of RoboMAX at SIMS 2021 Artifacts track. This is Mehrnoosh Askarpour, and in this video I will introduce our robotic mission adaptation exemplar collection. You can see the list of my co-authors on this page and also our emails, so please contact us in case you have any questions or you want to contribute to our collection. First, I will talk about the necessity of a repository like RoboMAX, and then I will talk about the structure of the repository and the type of data that we collect. Then I'll briefly describe our methodology to collect the exemplars. Then we will see some statistics and conclusions derived from the current state of RoboMAX, and finally we will see how you could contribute to it. So let's see why we need it. Recent advancements in robotic systems have let them set foot in several domains including industry, healthcare, and many others. Consequently, the executing tasks are complex and possibly in collaboration with human operators or other robots. Besides, the operating environment in a realistic setting is usually exposed to multiple sources of uncertainty. So the control software of these applications need to perform monitoring, analysis, planning, and task execution, all in a self-adaptive manner. And in turn, we need software engineering methods that make it possible. And for that, we need a clear understanding of self-adaptation requirements. However, one challenge to specify these requirements is the lack of models that practitioners and system designers can refer to in order to build up a comprehensive understanding of these requirements. To fill this gap, we propose RoboMAX, a repository of robotic mission adaptation exemplars that we collected from the robotic community. It could be used to develop, evaluate, and compare self-adaptation approaches for robotic applications, and hence bring together software engineering methods and robotic community needs in order to introduce effective and practical self-adaptation techniques. So let's describe the structure adopted for the exemplar definition. Each exemplar revolves around a model problem. Besides a description of the underlying scenario, each has some meta-information to explicitly record its features. The scenarios are classified in a way to precisely define the context where the scenario takes place, describe robotic system peculiarities, and highlight adaptation needs. Each exemplar is described in terms of the aspects we are about to review. Just keep in mind that we collect this information about each exemplar from end users who are basically robotic practitioners. And while doing that, we provide them with enough information, including detailed definitions and examples of each of these aspects, unlike here that we just briefly go through them for the lack of time. So let's review these aspects. First, a high-level description of the scenario, its environment, and the expected behavior, all in plain English. Then the source of the scenario, whether it comes from academia or industry, the application domain, such as healthcare or manufacturing, the number of robots in the system, meaning whether it's a single robot or multi-robot application, and description of robot features and their core hardware and software components and their specification, technical capabilities that are higher order capabilities enabled by robot features, and operational capabilities, which are conceptual concerns including cost, time, etc. We followed the uncertainty sources identified by Mahdavi et al. In 2017. Uncertainties could rise due to the modular state, such as incomplete or incorrect information, adaptation functions, such as coordination functions, the mission itself that could be poorly specified or could even change over time, changes of the operating environment at runtime or interactions with human operator or other robots, and dynamic robot capabilities that could change or extend over time. Finally, for each exemplar, we identify self-adaptation properties following the classification of Burns et al. In 2009, which covers self-management, stabilization, healing, and all the others mentioned on the slide. Definitions and examples of each of them is presented in the paper. We also collect a description of adaptation concerns, targeting the impact of different sources of uncertainty on the system, such as performance factors, timing, utility, or cost. So now that we know what is the relevant information for each exemplar, let's see how we collect them. We have a publicly available questionnaire with several questions concerning the aspects we just introduced. Robotic practitioners could fill the questionnaire and submit it. Once they do that, we will review the inserted data, see if clarifications or modifications are needed, and we reach out to the providers and ask for the required changes. And after possibly a few back and forth iterations, we will end up with a curated exemplar that we can add to the repository. Like I said before, we provide the end users detailed questions with definitions and in some cases examples. For instance, here is a question from our questionnaire, which is asking about robot features. Each feature is represented as an option, so we are enabling the end user to insert the information we actually need. This way, structuring each exemplar for the repository becomes way more agile. And obviously, for some of the questions, depending on what they ask for, multiple options could be selected. In addition to our options, we allow the users to add extra data that does not fit in our current classification. Observing this information could bring to our attention features that are worth being in our exemplar structure, and we can eventually enrich our questionnaire with more options. Let's see the current state of RoboMAX. We have 11 exemplars. 6 of them are collected from industry and 5 of them from academia. These 11 exemplars consist of 8 single robot scenarios, 1 with a team of robots, and 2 with single robots that could be also extended to multi-robot cases. The domain we have tackled so far are medical, food supply, household, and logistics. Some of the medical scenarios overlap with other domains, as the pie chart shows, which are educational, household, logistics, and emergency. We do not have time to discuss all the stats and derivations, but I encourage you to read them from the paper. Here we only show perhaps the most interesting lesson learned from RoboMAX so far, where the distribution of uncertainty sources over 11 exemplars is represented. As you can see, each uncertainty source has some sub-items, again following the classification of Mehdavi et al. In 2017. Sensing caused by imperfection of robot sensors, and model drift caused by discrepancy between the state of models maintained by the robot and the actual state of the robotic applications are the main 2 sources of uncertainty caused by model or state. Adaptation function uncertainty, pink bars, is majorly due to decentralization and coordination, which is caused by decision-making of robots in teams or swarms. In terms of mission uncertainty, the most observed source was lack of determinism and clarity in the mission specifications. Human in the loop was the most environmental cause of uncertainty. And finally, changing capabilities was the only capability-related source of uncertainty, as opposed to new or defined capabilities. Please note that this chart could look very different once we have many more exemplars in the repository, and it only is a representative of the current inserted exemplars. RoboMAX is a means to help the robotic community, but it also needs the help of community to grow. As the number of its exemplars increase, its stats and results become more reliable and comprehensive. So if you happen to work with well-defined robotic exemplars, please consider submitting them to our questionnaire, which could be reached by the first link. You can find useful instructions at the second link, and the last link is an extensive spreadsheet explaining the current exemplars already inserted and curated in RoboMAX. Thank you for your attention.